Hi there, Andrew Jackson, AJ Design Studio. One of my subscribers asked if I could do an explanation of the setting up curves in Solidworks. So this video I'm going to briefly go over the Style Spline. I'm not going to cover the old spline because there's lots of information about that online. The Style Spline, the terminology and the type of splines are interchangeable between other software like Rhino, so I find this quite good to use. So if you're in a sketch and you click Style Spline, the first thing that pops up is whether you want to create a Bezier curve, a B-spline with a fixed degree of 3, 5 or 7. So without going into much detail, go online, have a look on the Rhino website. There's a great explanation about curves and multiple span and single span curves, surfaces, etc. I'm not going to cover that here because it's much easier to just go and read what the experts have written. But basically a Bezier curve is a single span curve, meaning it has, say it has a degree of 5, it will have degree plus 1 equals the total amount of control points or control vertices, including the endpoints. So if you go Bezier curve and draw, so I've drawn 6 points, so if I pick on that curve, it'll say curve degree is 5. If I go changing this, you can see the control points go down and count. But another thing you might have noticed as I did that, you reduce the curve degree, so the control points are degree plus 1, so 6. As I go down, the curve changes in shape. Okay, where I get to degree 2, can't get any lower in SolidWorks, which is a line, degree 1. But if I go up, you notice the curve stays the same. So basically, if you've got a Bezier curve, single span curve, you can increase the curve degree and by doing so increase the amount of control points and it will retain the same shape, but you can't go the other way. So I can't go like this and then reduce the degree without the shape changing, but I can go like this and then add more points and the shape stays the same. Okay. Right, so this is a single span curve, degree 3. If you want to have independent tangent controls on each end of spline, tangent C requires the end point and the tangent point, which is the second one in, be able to create a tangent constraint that is independent from the other end. So I can go tangent, and this can move around, and the control points on the other end do not move. So I can create another tangent constraint on this end, which is independent from the other end. Okay, so if I move this around, the control points on the other end do not move. Now I can, if I want to delete one of those points, you can have a tangent connection with only, on each end, with only a degree 2 curve, but there's no inflection in a degree 2 curve, so the curvature is all one direction. It's like so. Okay, but now there's only one control point in the middle, and each end depends on the other. Okay, so if you want to create a spline that's curvature continuous, constraints at each end, the minimum degree is a degree 5 because you need 4, 5, 6 points. If you want each end to be independent from the other, then you need, there's our first point, positional, second point for tangent, and you need the third point, which is the curvature continuous point. So same on this end, 1, 2, 3, and you can see curve degree 5. So if I'm create equal curvature and equal curvature. I'll just freeze these lines. Okay, so because this is curvature continuous to a line, you can actually just make these collinear. I just wanted to illustrate that our spline there, each end is independent. Right, so instead of creating a spline between two lines, I will now show creating a style spline, curvature continuous on each end between two arcs. So insert style spline Bezier, I'll go 1, 2, 3, 4, 5, 6 points, and then I'll make equal curvature constraints on each end. And you'll notice now if I move tangent point, the curvature point moves around, and vice versa. If I move the curvature point, the tangent point moves around, because Solidworks is doing this. Oh, look at that. Isn't that interesting? According to that curvature graph, that's just a tangent connection at that end. I wonder what's going on there. Probably because I've got different curvature scales on in each sketch. We'll just go over to pop over to this sketch, turn off curvature combs, go back into this sketch. I'll convert entities and then turn the curvature graph on for these arcs. Okay, hey presto, problem solved. So that was different scale for the curvature graph in each sketch, even though I didn't change the scale. Must just automatically change it. Okay, so as I was saying, you move the curvature point, the tangent point will move accordingly to retain the curvature constraint there. So when I'm using splines like this, I like to dimension, sort of drag it out roughly, and then dimension from the end point to the tangent and the curvature point. Because it gives you more control over the spline by tweaking. Whoops. So now you can change the spline, this length of the control polygon, and the curvature point is updating, but it's not running around sort of randomly. Okay, and this way, doing this, you can sort of fine tune if you want to try and get a smoother connection between the entities. Okay, I think what I'll now talk about is what the difference is between, you would have noticed in the style spline, I only talked about the Bezier curve, the spline type, which is a single span. Now I'm going to talk about the B-spline, the degree 3, 5, 7, etc. So what I'll do is I'll create a degree 5 Bezier curve, so that's got 6 points. Okay. And just drag it out a bit. Turn the curvature graph on. Okay. And now I'll create another sketch on the front plane. Just delete this earlier stuff. Front plane sketch. Turn on our degree 5 Bezier curve. Now I'm going to add a style spline, and I'll pick B-spline degree 3. So what I'm going to do is, these are multi-span curves unless you've only got one more point than the degree, which makes it a single span. So in this case, degree 3, but we're going to have 1, 2, 3, 4, 5, 6 points. So it will make it a multi-span curve. Again, if you want to know more about single and multiple span curves, have a look on the Alias Golden Rules site, or the Rhino site has a really good explanation. So 1, 2, oh, it started there. Oh, let's try again. And I'll make the points coincident to the control polygon on the single span curve. Okay, now what you can notice there is the curves are quite vastly different. The reason behind that is with the multi-span curve here, it's basically segments of degree 3 curve, which means if I get this point here and move this around, you notice this end of the curve basically staying completely still. It's not moving at all. It allows you to have more points in a curve, and the influence of each point is much more localized than it is in a single span curve. Like if I go over into the other curve, like if I drag this point around, it affects the entire spline. Single span, you drag a point around, it affects the curvature across the entire spline. We go into our degree 3 spline with 6 control vertices. That change on this point is localized. You can see the curvature graph here not changing at all. But one other thing you might notice about the curvature graph is sort of some lumps happening like this. So a single span curve, there is no internal discontinuities because the curve is a single smooth curve right the way through. Okay, so you notice some discontinuities internally. So basically the highest continuity you can have internally in a multi-span curve is the multi-span curve degree. So in this case, you see there it says next to the cursor 3. Degree 3 minus 1 is G2. So that's curvature continuous is the best you can get as far as internal continuity. That's why he's saying this sort of peak here. But as you noticed, I bring up my background curve again. If I match these CVs up, oops. Each control point has more effect on the curve. So the higher the degree in a single span curve, each point has less effect on the shape of the curve. But in a say a degree 3 B-spline, you can bang out lots of points like this, and nothing over here has any effect on the back end of the curve here. Whereas if I was to make that as a single span Bezier, okay, you can see what's happening here. If I put the curvature graph on, if I move this point here, it's changing the curvature over here, right? So every point affects the whole curve. And it's much harder to get tighter curvatures. But then again, there's no discontinuities internally within the spline, whereas if I turn the curvature graph on here, you can see a whole lot of discontinuities, okay? So I pretty much never use these multi-span B-splines in Solidworks. Pretty much always use a Bezier single span curve. It's just the way I've set up myself to work, and also in Rhino. Okay, so if you want to create a B-spline degree 5 with multiple points, you will notice, if we turn the curvature graph on, the graph's much smoother. That's because the internal continuity is the degree of the multi-span curve minus 1. So this has got G4 internal continuity, which is pretty smooth. You can have a long spline with lots of control points, and tweaking this end over here doesn't affect the curvature elsewhere. So depending on what you're trying to do, this could be quite useful. Right, I'll just cover another scenario as where you're using a spline or an arc or something conic. You're modeling a half and you're coming off the center line. So let's just say we've got, let's pretend we've got a curve down here that could be a surface or a curve where we want to come off that curvature continuous, and then the center line we want to make it normal to the center line because we're going to mirror. Okay, so we want curvature continuous constraint off this geometry, and then horizontal constraint here. So that means we need 1, 2, 3 points on this end, or 5 points in total. So 1, 2, 3, 4, 5, because we want this independent. Okay, so coincident there. Curvature continuous. We'll just check that that is, yep, that second point moving. And we want this to be horizontal. I'm going to mirror this over. Let's just bring up our curvature graph. And I know people go, well, why aren't you making it curvature continuous to a line here? Because you're going to mirror that across. Well, because when this gets mirrored, it's matching itself. It's not matching a line. So if I was to make this curvature continuous to a line here, the curvature will go down to 0. Probably end up with a flat spot there. So I'll demonstrate what I mean. So if I go okay with this, let's extrude this and then mirror it. Okay. Go on the front plane and convert entities, and then bring up curvature graph on these. You can see there that's curvature continuous constraint, even though this was tangent, because this curvature, once you mirror it over, the curvature there and there is the same once it's mirrored. So that's why you don't want to put a curvature continuous constraint to a line here, because we're not matching to a line once it's mirrored, we're matching to itself. And I mean, you can tweak the geometry there, like there is a peak in the graph there. It is curvature continuous because the graph isn't stepping. If it was stepping, that means it would be tangent. Yeah, so you can get a bit smoother. I mean, curvature plot, the curvature is the same because it's matching. So conic's great if you're going to go like a full corner, you know what I mean? So rather than flat corner flat, you're just going to go right through like a full corner. So front plane here, sketch, then we'll make a conic, endpoints, and then I need to create 2 lines, one vertical, one horizontal, that the conic is tangent to, and both of these planes will be mirror planes. So the curvature from the conic here will be curvature continuous once it's mirrored over. And then row 30.65. Okay, just to demonstrate what I mean. If I extrude this and then mirror it twice, by sketch on the front plane here, convert these entities, and then go to the curvature combs. See how there's no step in the curvature comb, that they're curvature continuous. So even though they have a tangent constraint or normal to the mirror plane, once that gets mirrored over, it's matching itself. So you don't need to have a curvature continuous constraint to a line, because that's unknown. A line isn't what it's going to match once you've mirrored it. Okay, one last thing I was going to show is Solidworks. Because you have the style spline like this, you can create, I know in the newer versions of Solidworks, I'm only on 2017, newer versions you now have a G3 constraint in Sketcher called the torsion something or other. Anyway, with the style spline you can create higher than curvature continuous connections to lines anyway. So because curvature continuous connection to a line, you just got to make all the CVs collinear. So I'm going to show you how to make a G3 corner. So for G3, that means we need 4 points on the spline for each connection. So in total we need 8. So that means we need a degree 7 Bezier curve. So 1, 2, 3, 4. 1, 2, 3, 4. And pick those. Control polygon sections and the line collinear over here. Whoops. Okay, then you need to mention it, constrain it somehow. You can also make a G4 corner. Solidworks Sketcher. If I accept this, hey, let's have a look at our G3 corner. Zebra stripes. I'm going to make that G4. Because you've got constraints on the control polygon, you have to add CVs by right clicking and going into insert control vertex. Okay, so now this has got curve degree 9. That's got 10 points. Right, so theoretically that's D4, but okay, you got to muck around with the length. Oh, collinear. Yep. Lovely. Okay, so you can do all this with just style spline without having to have the torsion constraint. Obviously, if you want to use more fluid form and 3D space rather than sweeps that go to lines, then you'll have to use the torsion constraint. Right, I'm giving myself a migraine looking at this. Okay, I hope that was useful. If anybody else wants any more explanation of curves, anything specific, then shout out in the comments. If you find this useful, please subscribe to my channel, and I hope this was Hope this was useful. Yep, thanks very much. Andrew Jackson, AJ Design Studio. Bye.